Hi, let's talk about the central limit theorem with a simple simulation in R. So we'll bounce over here to the chapter and note that we are talking right about up here where we're looking at the central limit theorem, and we have a sample xi from I equals 1 to n. This is a random sample from a population with a mean of mu and variance sigma squared. Could be normal, could be chi-squared, could be right skewed, could be left skewed, could be bimodal. Any population, any distribution. Then a large n. Then for large n, the random variable, this transformation, x bar minus mu, divided by sigma x divided by the square root of n is known as the z-score, and we'll have an approximately normal distribution. It becomes more approximately normal, more normal as n gets larger and larger, with mean 0 and variance 1. And we'll see that today. This is often how hypothesis tests are run and how p-values are obtained from hypothesis tests. This special note that the standard error of x bar, which is this piece right there, that piece is the standard error of the x bar, is basically the uncertainty in x bar. It's its important interpretation is that its typical amount by which x bar tends to differ from the true mean, because we don't expect the sample mean to be exactly the mean of the population. We expect it to be close, a little bit bigger, a little bit smaller. But how much does it vary around that mean? It's the proxy for that, and the measurement of that is the standard error of x bar. So typically we don't know this sigma x, so we'll use this sample standard deviation. But what we're going to see is we'll generate an actual population. So let's, through simulation, right? We have this nice little laboratory. We can generate whatever population we want. So I'm going to go ahead and do that. And you'll see I'm pulling from a chi-squared distribution. And I've got like 1 million or 10 million of these here with 2 degrees of freedom. That's going to give me a mean of 2 and a standard deviation of 2, as you can see here. And so that's going to be our population. We have this very right-skewed, noticeably right-skewed distribution. Now notice I have N1, 10, and N2 is 50. I'm going to actually take 2 samples each time from this distribution to show the difference between x bars, between sample means of size 10 and sample means of size 50, where that makes a difference, what sufficiently large means. We're going to simulate this 1,000 times. So great. So what we're going to need to do is have a place to hold our x bars, because what we're going to do is generate, for this simulations time, 1,000 times. So I'm going to come in here and pull a sample of 10 and take the sample mean. And then I'll pull another sample of 10 and take the sample mean. And pull another sample of 10 and take the sample mean. And I'm going to do that 1,000 times. So at the end of the day, I'll have 1,000 sample means, each that came from a sample of size 10. And I'm also simultaneously going to do that for into a 50, for a sample size of 50, right along. So I'll have, each time I'll put one in x bar holder 1, which is an array, and x bar holder 2. So these will hold the 1,000 sample means of size 10, and these will hold the 1,000 sample means of size 50. So, okay, so we want to get these going here. So we'll create those. So now those holders exist. And this is going to take a little time, so we'll discuss what this is doing while it's moving. Okay, so now we're running a for loop for I and 1 to simulations, where we know simulations is 1,000. So for I and 1 to 1,000, it's going to say sample 1 is going to hold the sample mean. It's just going to take a sample from the population. Sorry, sample 1 is just going to hold the sample. It's going to sample from the population 10 times, because N1 is 10. It's going to take a random sample. And then sample 2 is going to take from the sample from the same population, it's going to take a sample of 50. And so it's going to, so I is 1. It's going to step through, take a sample of 10, a sample of 50, and then it's going to take x bar 1 will be the mean of that sample that I just pulled of 10, and x bar is going to be that mean of sample 2, which is the sample of 50. So I'll have 2 x bars, and then I'm just going to say x bar holder 1i, right? Index that with, right now it's 1 equals x bar 1. And x bar holder 2 of 1, the first slot, will be the second x bar from that sample of 50. And then I'll say, oh, that's it, and come back up to the top here. Okay, now I is 2. So I'll come back through and take another sample of 10, another sample of 50. I'll take the mean of the 10 and the mean of the 50, store them, and then I'll put them in the holder. This time it's slot 2, and this time it's slot 2. Then I'll come back up here. I is 1, now I is 3. Sorry, so I is 3, and I'll keep letting I be 4, 5, 6, all the way to 1,000. I is 3, I'll take another sample of 10, another sample of 50, a mean of the 10, a mean of the 50, and then store it. So it's finished here. So now at the end of the day, just to show it, if I was to do X bar holder 1, then there would be my 1,000 sample means. Right? We know that the true mean is 2. We see some get way above 2. Some are below 1, or below 2. So we want to know what the distribution of those 1,000 sample means were. And so that's why we have a nice little thing called the histogram here. And we'll do that. So hold on, ready, and mark the set. Check this out. So note that even though this was a chi-squared distribution to begin with, the sample means are both largely normal. Now note, this might have a little bit of a right skew on it, right? It's kind of like 2 bars to the left of this, and then there's 3 bars, 4 bars. Looks like there's a little more of a tail on this side. That's because I only sampled 10, right? I only sampled 10, that's less than 30. 30 is just kind of arbitrary number. Normally 30 is large enough. This is only a 10, and I'm pulling from a non-normal distribution. So I don't expect these to be, I expect to see a little bit of significant difference from a normal distribution. But these were a 50, and that looks pretty consistent with a normal distribution. If I sampled 100, it would look even more consistent to a normal distribution. So, but notice that these have mean of 2, right? So we came down here, we made our holders, we took our samples, and we made our histograms. And now we can look at the mean and standard deviations of each of those 1,000 sample means. So for the when n is 10, note that the mean is right about at 2, maybe a little bit lower, 1.94. And the standard deviation, that's the standard deviation of X bar holder. So let's talk about that. So this first one is X bar holder 1, right? And this one here is X bar holder 1. So the mean is right about at 2, maybe a little bit less than 2, again, because it wasn't quite enough to have the essential limit theorem have enough information to fully kick in. But still, that's pretty close to 2, the sample, the average of the sample means. And this guy here, remember that the standard deviation was 2, and if I look at 2 divided by the square root of 10, which is the standard error, sigma s divided by the square root of n, then that'll be about 0.63, that's about 0.63, 0.64, so 0.63, that's right about what it should be. Now note, when I get more information, the central limit theorem should perform a little better, and sure enough, this is a little bit closer to 2, which is what we know mu to be, mu, the population mean. And again, if I do 2 divided by the square root of 50, then I'll get pretty close to what I have here, 0.279, 0.282. Those are pretty close to each other. So that is the central limit theorem through a simulation. Now the last thing I should have been doing while we did this, it's going to take a little time, is I'll run this and explain it. Notice though that these are at mean 2, and standard deviation, the standard error is sigma divided by the square root of mean. This time 10, for this one 50. If I run this code, note here that what we're going to do is change them into z-scores, because remember we were talking about this z-score. So we just looked at the distribution of x bar. But what if I wanted to have a standard distribution here of mean 0 and standard deviation 1? But I have this population once again. In fact, this is a chi-squared distribution. So if I want to make this transformation, what I'll do is say, oh, I got z bar holder 1 and z bar holder 2, again for sample size 10 and sample size 50 is what I'll be working with. For I in simulations, I'm going to take a sample of size 10, I'm going to take a sample of size 50, I'm going to take an x bar of the 10, an x bar of mean of the 50 observations, and then I'm going to also take their standard deviation. So that's the standard deviation of the sample of 10, the standard deviation of the sample of 50, and then I'm going to make a z-score. So that's the z-score. I'll call that a z-score instead of a z-bar. So z-score of 1, z-score of 2 is equal to the mean, x-bar, the sample mean, minus the mean of the population, divided by S1 divided by the square root of 10. That's the standard error, and that is the x bar minus the mean of the population. That's exactly what this is. Right? X bar minus mu divided by, I guess we're down here, x bar minus mu divided by s divided by the square root of it. Okay, great, but what am I going to do with that? Well, I'm going to, just to make this make sense, we have x bar there. We'll make this bar z-score holder 1, z-score holder 2. Right, so I'll store them. And then it's going to loop back. It's going to say, okay, now let I be 2. Take another sample of 10, another sample of 50. Let's take a mean of 10, the mean of the 10 samples, the mean of the 50 samples, the standard deviation of the 10 samples, the standard deviation of the 50. Now let's make a z-score, x bar of the 10 minus overall mean, x bar divided by the s of the 10 divided by the square root of 10. Same thing for the 50. So we're just transforming x bar here minus mu divided by s divided by the square root of n. And we store them. We're going to put into x. We're going to put 1,000 of these in there. It's going to loop through here 1,000 times. I equals 1 all the way up to 1,000. So it's going to do this 1,000 times. Store it in z-score holder 1. Store the 50 from sample 50 in z-score holder 2. And then we're going to plot them. That's what you see here. Let's check that out. And checking this out, this does not look like a normal distribution. But that's because we had a non-normal distribution way back here that we were pulling our samples from, and the central limit theorem didn't have enough to kick in. If we would have pulled from a normal distribution, we don't need more than 30, or we don't have a sample size requirement if this is a normal distribution. And the closer it is to a normal distribution, the less we need. But with this chi-square distribution, we need a little bit more than 10. But at 50, it's still a little less skewed here, all right? So maybe even at 50, it's not quite enough, but maybe this is a good approximation. It's certainly a better approximation of a normal distribution than this one is. And if we would sample more than 1,000, this might fill in a little bit better too. But this is very, very useful. This is, let's check out the summary statistics. It should be close, the 50 should be close to having, this is the 10. It's got mean, right, a little bit less than 0. They should have about mean 0. So mean 0, standard deviation is a little bigger than 1, right? And at 50, this is closer to 0, still a little bit farther from 0 than I'd like, but that could be just due to the fact that we only took 1,000 samples. But that's certainly closer to 0, and that is much closer to 1. This, by the central limit theorem, should have a mean very close to 0 and a standard deviation very close to 1, which, relatively speaking, it does. So that is the central limit theorem through an R simulation. Great work.